In the previous video, we talked about stoichiometry and its practical applications when it comes to studying chemical reactions. Today, we're going to continue that discussion as we look at limiting reactants. The last time we were here, we discussed how stoichiometry helps us establish quantitative relationships between the mass of reactant used and the mass of product yielded. In all the reactions we looked at, we made one major assumption. We assumed that each reaction occurred cleanly. When we use the word cleanly in reference to chemical reactions, what we mean is that the reaction uses up all the reactant in the process of producing the products. In other words, there is no leftover reactant by the time the reaction ends. If we think back to our cooking example, we can consider the case of sugar cookies. Let's say we're trying to bake 10 sugar cookies. We'll need different amounts of flour, sugar, butter, and so on. This particular recipe is recommending 1 cup of sugar. But if we have 2 cups of sugar available to us, we can follow this recipe to the letter and still end up with 1 extra cup of sugar that we didn't use to make our cookies. Because of this, the final result will include the 10 sugar cookies as promised by the recipe, but it will also include the 1 extra cup of sugar we didn't use. In this context, the 1 extra cup of sugar is the leftover, and in chemistry, we would call this unused ingredient the excess reactant. So, to recap, most chemical reactions proceed until one particular reactant runs out or is consumed in its entirety, and sometimes there are leftovers. The limiting reactant is defined as the reactant which limits the amount of product that can be yielded. Another way of saying this is that when the chemical reaction ends, there is no more of this reactant left. It is completely consumed, and when this happens, the reaction stops. Now, once a chemical reaction stops, there might be other reactants that are left over. These reactants are referred to as excess reactants. Any given chemical reaction will have only one limiting reactant, but there can be multiple excess reactants. We have to consider the influence of limiting and excess reactants in stoichiometry in order to be truly accurate to real-world chemistry. The sort of stoichiometry we discussed last time, the sort where limiting and excess reactants are ignored and every reaction is said to react cleanly, this type of stoichiometry is usually called ideal stoichiometry. The problem, of course, is that real life is rarely ideal. Our practical interest as chemists, though, lies in identifying the limiting reactant in a given reaction. There are 2 methods we can use to accomplish this. The first is the reactant method. This method asks us to determine how many moles of each reactant are involved, and then compare the actual molar ratio of reactants to the ideal molar ratio of reactants. The second is the product method, which requires us to calculate how many moles of product are yielded by each reactant. The reactant which produces the least product is the limiting reactant. There isn't a huge difference between these 2 methods, and both will give us the same answer. Both will start with the amounts of reactants, so it's important to either note these down or calculate them using stoichiometry. The one you use just depends on which one seems more intuitive to you. Also, one important note here. No matter which method we use, we should always triple check to make sure that our chemical equations are balanced. If the chemical equation we write down is imbalanced, it doesn't matter how well we do the calculations. If the equation is wrong, everything is wrong. An even more important note is that the limiting reactant is not simply the reactant we have less of, nor is it just the reactant with the lowest stoichiometric coefficient. This bears repeating, honestly, so let me say that again. The limiting reactant is not just the reactant we have less of, and it is not just the reactant with the lowest coefficient. There are no shortcuts here. With that said, let's get into our 2 example problems. Example 1 says, about 5.8 grams of nitric oxide reacts with 10.2 grams of ozone gas to yield nitrogen dioxide and oxygen gas. There are 3 parts to this question. Part A, would like us to identify the limiting reactant. Part B would have us determine the mass of nitrogen dioxide formed, and Part C wants us to determine how much excess reactant remains when the reaction stops. Please pause this video if you'd like to try this for yourself. Let's go out of order and use the product method for this one. I personally prefer this method since it's always made more sense to me, so let's see what we can't do with it. For this procedure, we need to determine how much product each reactant produces. First, we'll need a balanced chemical equation. If we draw on our knowledge of chemical nomenclature, we'll end up with a chemical equation that looks like this. This equation is already balanced, so we don't need to do anything with it. Instead, we can jump right into the product method. Let's start with ozone, which has a chemical formula of O3. We have to convert 10.2 grams of ozone into moles of ozone using the molecule's molar mass, which is 48 grams per mole. We then multiply this by the molar ratio of nitrogen dioxide over ozone, which is just 1/1 according to our equation. There we are. We get 0.213 moles of nitrogen dioxide produced by ozone. Let's move on to nitric oxide, or NO. 5.8 grams of NO multiplied by the inverse of the molar mass of NO, (30 grams per mole, multiplied by the 1/1 ratio of nitrogen dioxide to nitric oxide. We obtain 0.193 moles of nitrogen dioxide produced by nitric oxide. Nitric oxide clearly produces fewer moles of product as compared to ozone, so we designate nitric oxide as our limiting reactant. That's our answer for part A. For part B, we have to find out how many grams of product are produced. This might seem confusing, but we have to remember that the reaction stops once the limiting reactant is used up. This means that we can use this number, 0.193 moles of NO2 as our basis for calculation. This expresses the product yielded in moles, so we convert it to grams by multiplying it by 46 grams per mole, the molar mass of nitrogen dioxide. Our answer for part B is approximately 8.9 grams of NO2. The last part of this question, part C, wants us to find the amount of excess reactant which remains. Because nitric oxide is the limiting reactant, we know that ozone is the excess reactant. Now, the amount of ozone remaining is going to be the initial amount of ozone minus the amount of ozone which is consumed in the reaction. Let's start with the initial amount. We know that we begin with 10.2 grams of ozone. If the problem specified that the answer to part C should be in moles, we would convert this. But since it doesn't say, let's go ahead and keep it in grams. Now all we need to do is find the amount of ozone which participates in the reaction. To do this, we use the molar ratio between the principal product, nitrogen dioxide, and ozone. We know this ratio is just 1/1 per our equation, so the moles of ozone are equal to the moles of NO2 produced, which is, again, 0.193, since the reaction stops as soon as the nitric oxide is consumed. We can convert 0.193 moles of ozone into grams pretty easily, multiplying it by 48 grams per mole to obtain about 9.3 grams of ozone. For our final calculation, we subtract 9.3 from 10.2 to get 0.9 grams of ozone, which remains after the reaction ends, and that is our response to part C. Before we move on, I did want to mention that this problem, the reaction of nitric oxide and ozone, is actually believed to have been part of the reason for depletion of atmospheric ozone. Nitric oxide is a common industrial chemical, and if it escapes as a gas into the atmosphere, it is believed that it reacts with ozone in the air to form nitrogen dioxide and oxygen gas. This lowers the amount of ozone in the atmosphere, which is unfortunate since ozone is responsible for keeping harmful ultraviolet solar radiation off the planet's surface and away from us. Alright, let's see if we can breeze through example 2 here. This problem tells us that hydrogen and nitrogen react to form ammonia, which is also called hydrogen nitride. For a reaction involving 10 grams of N2 and 6 grams of H2, determine the limiting reactant. We'll use the reactant method for this question just so we have some exposure to it. Our first step is to write out a chemical equation. H2 plus N2 yields NH3. We can use trial and error to balance this. If we put the coefficient 2 in front of NH3, that balances it with the N2 over here by creating an equivalent number of nitrogens on both sides. We can then add the coefficient 3 in front of H2 to balance the hydrogens. That's our balanced chemical equation. Our next step is to convert these gram amounts into moles using the molar masses of diatomic hydrogen and diatomic nitrogen, which are 2 grams per mole and 28 grams per mole respectively. We have here 0.357 moles of N2 and 3 moles of H2. We now create 2 variables, A and B. The molar ratio between B and A is 3 moles of hydrogen for every 1 mole of nitrogen according to our equation. So we multiply 0.357 moles of N2 by 3 moles of H2 over 1 mole of N2. This gives us 1.071 moles of H2. This value here is our ideal or hypothetical amount of B. But our actual amount of B, according to our given quantities, is 3 moles of H2. Now, if the ideal amount of B is higher than the actual amount of B, then B is the limiting reactant. One more time. If the ideal amount of B is greater than the actual amount of B, then B is the limiting reactant. The ideal amount of B is 1.071 moles, but our actual amount is 3 moles. The actual amount is greater. So B, or hydrogen gas, or H2, whatever we want to call it, is not our limiting reactant. Our only other reactant, nitrogen gas, has to be our limiting reactant. As I said, the reactant method shown here isn't as intuitive to me as the product method we used in example 1, but this is a personal preference thing. Some people may well prefer this method here, and that's totally fine. One final note. Some textbooks might refer to the limiting reactant as the limiting reagent. The word reagent basically describes any chemical used to instigate or analyze a chemical reaction, which usually makes it the same as a reactant, so these terms are used synonymously. We shouldn't be thrown off our guard if we see limiting reagent instead of reactant. That's all we're trying to establish with this point. In the next video, Unit 3, Video 5, we're going to conclude Unit 3 with a discussion regarding reaction yield. Thank you for watching.